Okay. Am I audible, Jyotirmaji?
Hello. Good evening, Shreji. Yes, you're audible.
Good evening, good evening. Let me also. Can you remove your video so that we do not have any bandwidth issue? Yeah. Thank
Sure,
you.
sure.
Thank you.
I have removed.
Yeah. I guess you have some questions to ask. Is that correct?
Yes, I have some questions to ask from the assignment. So can I share it with you on the chat?
Uh, yes, you can start writing or just sharing the screenshots on the chat. We try to open them and discuss.
Okay. Uh,
Right. Yes, please tell me what is the doubt?
Actually, while estimating the steam consumption, the question says that we must estimate the steam consumption ratio. So in this case,
Wait, wait,
I am
wait, wait.
unable.
So I have some issues. I think I can't hear you very properly. Let me just give me a second. Yes. Can you try to speak again?
Yes. So my doubt in this case is that how do we calculate the steam consumption value?
Steam consumption.
Because
So
the
what is the unit here? Yeah.
because the
Go
answer
ahead.
that I have given, maybe from my previous calculation, that is not matching with the given option. So I just wanted to see what is might be the procedure and what is the value.
Okay, so let's just first discuss how I would approach this problem, and then if your approach and my approach are different, then yeah, then let's go into the specifics. So let's just try to see what is this problem about. So a dry saturated steam with a pressure of 10 bar enters into the cylinder of a reciprocating engine where the steam expands to 1 bar. That's okay. Then the pressure decreases to a back pressure of 0.25 bar at a constant volume process. So from 2 to 5, I think 2 to 5 is okay, let it be. So yeah, estimate steam consumption. This is the first question of a multi-part question, is it? Jyotirmaji? Is this a
Sorry,
complete question? Do we need
so,
anything else?
sorry, I was muted. So this is a four-part question. So this is the first part of the question. We have three more parts.
Okay.
So
Okay.
maybe I can also attach the snap.
Yes, you can, but does it say anything about where 2 to 5 is the expansion process? I believe. Is it the
Well,
case?
as per my understanding, while solving, what I did is that P1 that is shown over here, I have taken to be the isobaric 10 bar line. Then at 5, there is one point. So in the figure, it is just shown like this. So I have assumed there is another parallel line going through 5 also between P1 and P3. So let that be P2. So that is 1 bar. And then the pressure decreases to a back pressure of 0.25 bar. So I have taken P3 to be 0.25 bar.
So from 5 to what is the process? It follows from 1 bar to zero point 0.5 bar, 0.25 bar.
One but two over here it is basically it is shown that back pressure of at a constant volume process. So basically from point 0.5 to point 0.6 we have a constant volume process.
Okay. So then
So
you are not.
yes, so basically in the calculation what I had taken is that since it's a constant volume process, so the specific volume V5 is equal to V6 that I had taken.
Just a second. The pressure decreases to a back pressure volume process. Constant volume process. Okay, fine. Yeah, that will make sense. Hmm. That's okay. Now it talks about steam consumption. Okay. Uh, Dry saturated steam with a pressure of 10 bar enters into the cylinder of a reciprocating engine where the steam expands to 1 bar. Okay. So 2 to 5. So the work producing process is 2 to 5 only, I guess.
Yes.
Uh, Now we need to find, and this is probably an isobaric process. We consider ideal thing, right?
2 to 5
Is it isentropic?
isentropic process, yes.
I said something else, it seems. Yeah, so
Iso
isentropic.
isentropic.
Yeah, because of no ideal, because it's an ideal process, let's say. So now you know the point two is well known. You know everything about point two.
Yes, point 2 and 1 is, yes, that's known.
Now you can find S2 and you know P5.
Yes, so from the chart we can calculate S2 and that is equal to S5, that is equal to 6.5864 kilojoule per kg Kelvin. So that is known. And then
Yeah.
from there we can say that S2 is equal to S5. Now let's say the S5 is at a particular pressure line. So we can say that in case of S5, let's say X SG plus 1 minus X SF. So from there
Hmm.
we can calculate the value of X, that is
Hmm.
for that particular isobaric line, which also comes out
Yes.
to be 0.87
Okay. So now you have 0.87 quality of steam. You can
at
also
zero point 0.5.
calculate, yeah, and you can calculate H5 minus H2 minus H5.
H2, 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 H2 minus H5. Yes, yes, we can calculate H2 minus H5.
Indeed, wait a
That
second.
should be the
So
work
for
turbine
a
work.
this is an isentropic process. For an isentropic process, TDS is 0, so DH equals to VDP, right? VDP, right? DH equals to VDP. But what is the work done? Work done is PDV, isn't it?
But
The
it's a
work
flow process, so we can say also like specific volume
it's
integration dP.
is it a flow process? Is it a flow process because it's a reciprocating engine? Let me just check. In a reciprocating engine, what is the assumed process between what is the expansion process assumed to be? Let me just quickly check that. Like in the diesel cycle, we consider them to be isentropic. This isentropic expansion and isentropic compression, right? In an
Yes.
isentropic compression and expansion, uh, what is Wn? Wn will be yes. So wait, W, wait.
Because while solving it, the answer which is shown over here, answer comes out to be 7.19, but mine is not matching. It is 10.25.
That is okay. If you think about how have you calculated this? How have you calculated? Tell me.
So basically, what I did is that what is the net work output that we have to take into account, and to get that, what I did is that first is the positive work that we get, that is H2 minus H5. So that comes out to be 391.7 kilojoule per kg. But then the back pressure loss we should also take. So for that, what I have done is that considering the because it is shown that then the pressure decreased to a back pressure of 0.25 bar at constant volume process. So what I did is that the back pressure loss, which I calculated, is specific volume into P3 minus P2, which is from P3 minus P2. So that I get the value W2. So basically WT minus back pressure loss, I get the value of work net. And that when we divide, because it is
Am
short,
I not
that,
audible? Hello?
uh,
Am I not
hello?
audible?
No,
Yeah,
I
am
can
I
hear
not
you.
audible?
Well, I
Yeah,
can
yeah,
hear
wait,
you.
no.
Okay.
Okay. Is there a lag or anything? Is there a lag or what?
Well, I can
Yeah.
hear you.
So let's go through it step by step in a like slowly. So your negative work or the work injection into the cycle will not be V P2 minus P3. Why is that? Why do you think will that be?
That means it's not a flow work. That's why. Maybe.
It's not a, it's no, no. Okay. So you're saying V, so what is the specific volume that you have taken in that expression when you say work N is equals to V into P2 minus P3?
So while calculating the various points, various properties for the point number 5, once we get the value of x, once we get
No,
the
no.
value of
What is
x,
V in your negative power, negative work done? What is the specific volume that you have taken? You told me that it is V delta P you have taken. What is the V that you have taken there?
v that I have taken, v is 1.4771.
No, what is which point is that? Which point is that corresponding to?
That's corresponding to zero point 0.5 over here on the graph.
Now tell me, why will it be V? Why V will correspond to 5 now? Your negative work. See, as far as I understand what you're trying to say. Let me copy this image and see what you're trying to say. Hmm. There will be some positive work which will happen between 2 to 5,
Yes.
right? The negative work, let's say, happens between 4 to 1, right? Where will the negative work happen? In which process is the negative work going to happen? Tell me that. Let's reduce that.
Then it should be between 4 to 1. Yes.
But you have taken V5.
Yes.
Okay, so that is one thing. The other thing here is, see, note that this from 4 to 1, uh, V will not be constant. In fact, V will be varying. You understand?
Yes.
Why, let's say, why we consider that V is a constant generally. In Rankine cycles, we will use that formula largely a lot of times. Why is that? I'm waiting for you to answer.
Well, I think maybe it's a closed cycle. That's why.
No, 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 no. So you should know why. See, this is something that you would require, right? Why VDP? No, no. My question is, let me ask the question again. My question is, in steam cycles, we use that work done is VDP, where we take some like some value we take at some point. V will be a constant, and we say that V delta P is the work done by the compressor or the by the pump. By the pump is the correct word. So pump work we calculate by V delta P. Why is that? See, let's understand this part. So, first of all, do you realize this? You tell me which one is correct, okay? VDP, will that imply that W is P integral dp? Which one is the correct formula? And when is this correct? Is this always correct? See, I know that you know most of it. So just answer like just let's have a discussion rather than me telling you the entire theory because I know most of it you already know. I know. Just let's quickly pinpoint where there is a small confusion or something so that we can quickly. So if you have confusion, then we can pinpoint it. Otherwise, if you're totally blank, then I will have to tell you everything from the starting. So tell me, just tell me what the things that you are sure of, you know things. So are you aware which of this is correct? Like which of this is wrong, or can we write any of this expression always? Or let me confuse you even more. Uh, which one is correct? You need to tell me this. See, because this is important. Right now, what we are doing is in your example, you study a chapter and you know the formulas written in that chapter and you apply them. But in the paper, it will be totally unclear which chapter this question is from, whatever what is going on. So at that point, you will be totally unclear what formulas to use. So it is important to understand where is this formula coming from, so that later on you can actually figure it out which formula is to be used, right? So that is why I am trying to push you here to find let's discuss this part. So just tell me which statement is always correct, what is wrong here, which statement. Let's first talk about which statement is universally correct for a simply compressible system. Which one is correct? Let me put this question. Or if you're clear about it, we can move forward. If you're thinking that all this I know, I'm just kind of repeating myself here, or repeating something which is already there, you can tell me that part also. For a compressible, for a simply simple compressible system, which one holds always? Tell me, Jyotirmay.
Well, and the number one, two, four, simply.
Okay, maybe.
Yeah.
You're saying anything? You
Uh,
confused?
a bit, yes. Sorry.
You're confused or
I'm a bit confused. So,
okay. So let me just quickly take some time and just clear it out for you. Okay. This is indeed very confusing in some ways, but it will get clarified easily. So I'll just tell you. See, the universal statement which holds is this, nothing else. Okay. This is the only thing that we can say for sure. Unless any other thing is specified, we can't say what is going on here. Okay. One thing is that if you recall from your few like early chapters, first of all, let's realize that the work has lot of causes. Like work can happen because of lot of things, and you would recall this. There was a boundary work, right? There could be an electric work. Uh, there could be a you remember you asked me a question regarding uh, number of modes depends on number of state variables will be number of reversible works can be done plus one or something. There was a slide which you asked a question from. You remember in the early sessions? You
Yes,
recall?
yes, I recall.
So you, if you would recall, we had a good discussion around about that also. Maybe I'll pull up that slide. Let me. Then there will be surface tension also. Now, why I'm trying to take a whole story, why I'm just quickly not telling you an answer is because you will get confused unless I tell you the entire story. So this is an entire progression over chapters, which expression to use. This W expression is indeed, it is important to tell you the entire story from the very start. So anyways, this comes up in the second chapter, okay? And let me pull up that slide. It must be somewhere here only. We call, we had this discussion early on. Yeah. See, so this is how we defined work done. You remember? And this was the phase rule we discussed, and this was because of the question you asked me at some point. Maybe that slide that image would also be here. No, let me check. It will be somewhere here, or maybe you presented it. I don't know. It's not here. I can't see it. But anyways, yeah, here it is. Okay, so first of all, we have to realize one thing is that fundamentally there can be multiple ways to look at work. Okay. Now the interest, and generally when we start with it, uh, we see that boundary work done. See, this is the fundamental expression. Okay, this is important. And actually there will be also this work also. It's important for me to write this. Okay, see, this is an expression which holds, always holds. So the expression that I'm going to write now is always holds. So the boundary work that you are doing will always be PDV. Why? Jyotirmaji, can you tell me now why boundary work is always PDV? There is no doubt in that. No matter which case you are dealing with, boundary work will always be PDV. Why?
So suppose if you have a piston cylinder arrangement, so in this case,
Yes. Yes, you were saying something.
yes, so because then yes, the displacement should be there. Otherwise, without that, it will be zero.
Yes. So when boundary moves, when your system boundary moves, it has to be supported by some force, and that force is in a simple compressible system, it will be the pressure force. And so FDX. See, actually, this is the case. In some sense, we can say this. Not sure if this is correct. Uh, but in case of a simple compressible system where all others are zero, you know that the force will be the pressure force and dx will be the movement of your volume or the displacement of a boundary, right? So that is there. Okay. So note that if there is a boundary movement, there will be boundary work done associated in that process, in that system. Okay. That is not going to go anywhere. Now, this we know that this will be VI, VD, DI. This will be some F into DB or something. But largely we don't deal with it too much. So we kind of ignore it. That is why people get confused. When some problem will come which has a magnetic and electric components, then you might get confused because I'm not elaborating on these two aspects. But in the interest of time and all, and assuming that or and uh, uh, just hoping that these things will not pop up in your final exam, I'm just kind of removing them. So remember that I'm kind of at this point. Let me write this part. Wait. So we start from here. So I'm just progression of expression for work. Okay, this is what we are talking about. This is the big heading. So up till now, this is for a compressible system. This will always hold. Okay, there might be other components which we are kind of neglected right now. We have not considered other components also. There might be other things also. Maybe let me see if there are other components. Maybe some concentration or something. I don't know. Some other physics that can come in. Now, the first step, neglecting or assuming no electric or magnetic work is in the process. Okay, we
Okay.
write this. What do we write? We write this thing. Similarly, if there is a surface tension, we then know surface tension into area. So sigma dA is delta surface, right? So we could substitute that, or if there is no surface tension forces, if those forces are negligible, right? If we are dealing with large amount of forces, then we can neglect this part, right? If there is no surface tension effects or anything, if there is no phase change boundaries or anything that are involved, you kind of neglect it. Okay, that is also a very engineering, like it's not always there, right? Surface tension, you don't deal with it too much. Another thing which you would now recall is that delta flow is VdP. So these two statements they always hold. You don't need to neglect or assume an electric or magnetic work. These two always hold. Can you tell me why delta W flow is VdP?
Well, if the basic expression that is there, W is equal to PV, that we differentiate, then the two terms come out. That is PdV minus VdP. From there we can derive.
Wait. Sorry, I've written it incorrectly. It's not VdP. It's dPV. Or it is VdP only. Let me think. Wait. It's dPV. Yes, dPV. PV both will come inside it. And I'll show this to you. Okay, I'll show this. Do you recall this part, this expression?
Yes.
Do you no? Please, if you're not able to recall, tell me so I can actually explain that part to you.
Well, it will be good if you can please briefly explain. It will also be
Yeah.
good for me.
So if you have a system, right, and say you are pushing some, let's say in a flow system, because now we are saying that there is a flow into your system. So there is a in stream and outstream. Let's say there is some mass exchange happening. See, in a control volume, you don't have any mass exchange. But when you have a mass exchange, some amount of mass will be entering your system, right?
Yes.
Now, for it to enter your system, it will have, so it will move, right? It will move. This ball, let's say this ball moves into your system, right? For it to move, it has to do some work. What work? So now that work will be what? It has to uh, what do you say, bear the pressure force which will be applying at the point of its at the point at the boundary. Say it is here, right? It starts to enter, it will start feeling that pressure that this system has. You understand?
Yes.
And now once it moves, so this P into this will become Once it moves in, actually, let me just quickly see. I also don't remember exactly how that expression comes. Wait, just give me a second. Flow work to see, to recall. Flow work. Just give me a second. It will take too much time. I remember that part. Uh, work done, work that you do. Hmm, give me a second. Let me call this part. So pressure is. Right. See, it will be applying some. See, this is the this is the right image to show. See, this is the right image to show. Um, okay. So basically, now it
Okay.
says imaginary piston and all. Just forget that part. Don't imagine any piston for now, because I don't like to use that terminology, imaginary piston or anything. And forget about this piston also. Let's ignore this piston part also. Right? Just assume that there is a pipe through which some mass is entering. So the cross sectional area through which this mass will enter is A, right? And say it enters with some mass, right? Now this when it will enter, there is no reversibility or anything. The pressure of the fluid which is entering, or the pressure of mass which is entering the system, will be equal to the mass of the pressure of the system itself. So this P and this PCV will be same, let's say, because you don't want any reversibilities here, right? We are talking about a reversible work. We don't
Okay.
want, right? You understand that point,
Right.
right?
Right.
So pressures have to be same. The reason pressure I'm saying pressure is same is that I don't want to bring any irreversibility into the system. Once I have any pressure difference, irreversibility will come. Non-quasi steadiness will come. Non-quasi staticness will come. So this, right? So the force it will experience will be P, right? Now what will be work? What will be the work done? What will be the work it is required? See this to enter this system, right? This to for this mass to enter this control volume or this system, it has to do some work for it to enter because it is experiencing some force, and there will be a displacement. You understand that there will be a displacement. What displacement it will be? It will be L. So force into L. So that will be again F dx, right?
Yes.
Now this F dx, what is x here? It will be V dV, which is the volume of the mass entering the system by A, right? And we are assuming that this F by A is a small, or this is what it will happen. And A is a constant. You understand this?
Yes.
And one more thing, actually, this should not be dV. It should be F into V. See, it should be F VA. So it is F dx, right? I write X. Now, the reason I will take F inside is, so why am I taking this thing inside? Let me think. F dx. Um, let me think. Let me think. Actually, this has to be dPV. It should come dPV. Let me just try to think how to explain it to you why it should be dPV and not PdV. Okay. So as I mentioned, it is F into x. Okay, there is no x, right? Let's say let's say some dm amount of mass is entering your system. Okay.
Yes.
So the work in that case, uh, yeah. So the work in that case will be, say it's entering dm amount of mass is entering. So now for dm, the work done will be F into dx, which is what dv by a, right?
dv
But
by
note,
a. Okay.
but note that this F by a, which is like P, right? This pressure itself is dependent on the amount of mass entering to the system. See, once this mass enters the control volume, the pressure will change, right? Pressure is not a constant here. Am I making sense or not? Let me think. Why this has to be actually this comes in the context of this thing. See, it comes in the constant context of this thing. Plus,
dv plus
actually, this is actually not even a, you say, not even an inexact. It is an exact work. Actually, this, because it is totally dependent on your. It's an exact differential. No, that is why it is not an inexact differential. Let me think. This is a when some amount of mass is entering your system, you have F into dx. That is what we write. Mm, then this will become PdV. Actually, it should become dPV rather than PdV. It will be by the actually this will be, you know what, this has to be written like this, df dv, or no, it actually has to be written like this, f dv plus vdf plus df dv, 2df dv. This has to be like this, or no, wait, why will this 2 come? No, wait, I'm writing things incorrectly. Oh no, it's fine. dv plus df v, you will have dv. Yeah, it has to be this actually.
It should be fdx. Yes.
Let me think. FDX is the work done because of the movement. Okay. Okay. So maybe I don't have a good explanation right now to tell you why it's dPV. Okay. But P and V both come inside the differential. For now, let's try to get this. Mm, I consider that part that it is a continuous process, then rate of change of energy happens and there is a flow rate. Now this, because of this flow rate, m dot comes. So I'm not able to justify why this has to be inside the integral. Okay, but largely even the books just do a quick maybe I have to ask ChatGPT or something so that I can get a good explanation of why this happens. But generally, I'll tell you in the book how it is written. It is written like this: force into X, right? And so it says P into V. They just say that workflow is PV, so D workflow is DPV. That is how they just quickly say this. Um, it is PDV plus VDP. Both of it is there. Okay, fine. Okay, so I think if we just go ahead and just skip this part, okay, because we are on discussing a more important aspect. Can you digest this line that workflow is DPV? I'm just not able to explain it, but it is this thing, okay, all
Okay.
okay, right?
Okay.
So now this is the case. Now, in the incoming chapters, now what happens in the coming chapters, okay? In the coming chapters, you first realize a closed system or control mass analysis. In control mass analysis, one thing is that because there is no flow inside your system, there is no mass, dm by dt is zero.
Yes. It's a
So
steady
work,
state flow.
yeah, steady state, and also it's not about steady state. Let me wait, let me correct this. It's not, this is not the correct thing. Control mass means there is no mass exchange. So it's not that it's steady state. This is also important. There is no mass exchange happening. Steady state can still be achieved for a control volume approach, right? For a control steady flow is a steady flow means that there's steady state, but
There
it's
is
not
mass
that
exchange.
it's a control mass. You understand? There's no
Okay.
mass exchange. Mass, it's the same mass. There is no mass exchanges happening at the boundary. So in those cases, there is no workflow. To actually see this, this will again take some time. See, dm by dt will be dot some. I don't even know if I will be able to derive this, but let me see if I can, because this will then get explained quickly. Even the study workflow will come in this thing. Like we can show this. Okay, now this is the thing. In this one, how do you write it? You write it like this: dE by dt will be, let's say there it's an idea, or let's say delta Q is there, delta Q is there. Now we start writing work done. So work done has to be like this. As you know, already know, H out, then H in also comes in, right? I kind of have used, uh, and then we write, right, TV. Yeah. And this is coming basically on delta. Um, how do I show this now? Okay, anyways, let's not get bogged down right now. Here, maybe I can explain it better later on. Just in this case, in the control mass analysis, okay, what happens? There is no mass transfer, right? No mass exchange is happening. So you read that streams have their own, what do you say? Streams have their energy is measured in enthalpies because they're flowing, and that is essentially because when a stream enters, no, when there is a mass entering your system, it's just not bringing its internal energy into your system. It is also bringing the work that is it is doing. So see, for any stream to enter your system, you will have to supply extra energy. Why? Well, that stream, no matter, see, this, let's say this is PV, and this is at pressure P, and this is at it is some volume V or some density V. The control volume is also having the same pressure and same volume, right? But why will this bunch of mass enter your system? You will have to do some work, right? To move it into your system, you have to do some work, and that work is actually dPV. Okay. Now,
Okay.
because there is no mass exchange, our essential expression becomes this, that we kind of say that this part is zero for a control mass system. And so this becomes PdV. Okay. In a control volume approach, in a control volume approach, if you would note, in a control volume approach, actually this holds. So there are both kinds of work in a control volume approach. It's not that in a control volume approach, uh, uh, anything goes away. Okay. Unless I say, you understand, right? Both of the work exists generally in a control volume approach. Unless I say that there is no volume, that the volume is not increasing or decreasing. Only then this thing goes away. If there is a volume increase, there is a volume change in the system, no, you will have to consider boundary work. But generally in a steady flow process, there is no volume exchange. dV by dt will be zero. There will be no motion. So that is why that goes off. You got my point?
Okay. So
Do I need to enforce that better?
no,
It's not
this
clear.
part is clear. Up till now it's
This part
clear.
is clear.
Control mass and the
It's
control volume.
clear, right?
Yeah. Okay.
Okay. Now let's go to the problem that you were facing here. Here, what will it be? It will be VDP. Okay. This will be V. This will be what? Wait. Yeah, this will be delta W boundary. Then comes another thing. Then comes delta W reversible. This is now comes another story.
Plus W
Reversible.
reversible.
Now, where does this come from? This comes from TDS relationship. Okay. First of all, you need to note that TDS holds for all, like TDS is an identity. It holds for always holds. For a simple
Yes.
compressible system, it will always hold,
Yes.
right?
DH minus PdV. Yeah. Du plus PdV.
Now, for a control volume, what happens is, if you have a steady flow, for a steady flow process, this is the case. dE by dt is zero. Okay. dm by dt is also zero. dm by dt is also zero. Okay. You understand that, right? There is no because it's a steady flow process. Indeed, your volumes are generally for a steady flow process, because your volume cannot also move. Then it becomes a transient process. If your volume is moving, then you are in a transient condition. dV by dt is also zero. This is also happening, and this is again, how is it? How are we writing this? Because we are saying that all gradients with respect to time have to be zero. You understand? So for a
Yes.
steady flow process, there cannot be any boundary work. Actually, wait, I removed this part, no? This should be there. Why did I remove it? I told you to that both of them will be there. For a steady flow process, you will not have boundary work. Why? Can you tell me now? Can you quickly tell me why for a steady flow process, boundary work will be zero? Jyotirmay ji,
Yes,
why will the boundary work be zero for a steady flow process? If you're
well, as
not
we
able to
said that,
understand,
because as we said that we are not looking at the bound, the system bound, as we see over the steady flow processes values over here. So we can say that for the steady flow process, the boundary is not involved, because I'm not looking at the piston type movement. So in this case, we can say that the boundary work is zero.
no, that is not correct. That is not correct. For a steady flow process, dV is zero. Over time, volume does not increase. So dV is zero. That is the reason. It's not that we are not looking at a piston type system. That is also true, but it is not fundamental.
Because dV by dt is zero. Okay.
dV is zero, no? So
Yes.
dV here you see boundary work is zero. Because for a steady flow process, volume should not change. Volume, if volume is changing, then you are in a transient conditions. If
Yes.
volume is changing with time, volume should not also change with time. It is a constant volume process, like constant total volume process, right?
Right.
Mass can enter and exit, but volume is not changing. So that is why this boundary work goes off. So that is one thing. Now let's substitute this thing there. Now we also know that for a steady flow process, this will hold. Now you look at it. What is this in this case? If there are no irreversibilities, then delta Q will be TDS. Do you agree?
Okay. Yes, we can say that.
There is no irreversibility, right? So this is the expression that we write, right? ds equals to t del q delta q by t. We can put a integration also here, integration or summation. That is okay. If we put summation here, then we have to put summation here also. And then you write plus s dot generation or s generation, isn't it?
Yes, we can say that. Plus
So
S.
then, because s generation is zero, this becomes TDS. Okay. You understand?
Yes, it's okay.
Now, if this becomes TDS and this has to be zero again, do you understand why this has to be zero? This was zero. The right hand side was zero. Why? Because it is a steady flow process. Now, if you will see, if you compare this, and again, it's a steady flow process, no? So m dot in and m dot out will be equal. So this will be just m dot. Okay. And this we can write as, what can we write? DH or H in minus H out, we kind of can write DH, let's say, if we write DH. Okay, if it's a single stream, in a single stream case, this is the thing there. What else is there? Let me see. It actually has to be del TDS, not this. It's a extensive property right now. Now, if you divide by m dot, you will get ds and dv. Okay, and
Okay.
so one more thing, yeah. Then I wrote PDV, right? Wait. Plus there will be some other work also. There will be delta reversible. There will be work done. There will be another work done. No, one is wait. What have I done? Let me correctly write things. correctly written things. Why am I doing this? Wait, just give me a second. Hmm. See, this is what you write. You don't write this. You don't write PDV. You write W. And this is reversible. Why am I writing reversible? Can you tell me? This is what I write. I don't write PDV. So PDV will not be there. That was the wrong statement because I was saying that there will be no boundary work, right? Why will PDV come? There's no boundary work. This is okay.
Okay.
Now you tell me why I have written reversible there. Actually, at this point, it's not required. At this point, it's not required, but here it is required. Reversible is coming because I'm substituting delta Q to be TDS. So I'm saying the process is irreversible. Okay, you
Okay.
understand?
Okay.
What it's there is a progression to it. I know this is a long thing and different expressions for W, but anyways, just bear with me. So now here you see, just compare these two expressions. So you will realize that delta reversible is actually this will TDS, and this is actually minus or what? This is minus, right? TDS
Yes,
equals
it's
to no,
minus.
minus, no?
No,
So this,
no,
wait,
yes.
wait, is it minus or I've forgotten?
It's not minus.
It is not minus, no, wait.
No.
It is just, it's not minus, yes, wait. So this will be TTS equals to DH. Because this is H in minus H out I have written, no? So DH we consider H out minus H in. And when generally we consider this, right? H out minus H in. This will be minus DH. Did you understand?
Okay, because okay, delta H. Okay. Mm-hmm. TDS minus TH minus TH TTS.
Is it still confusing?
No, it's okay so far.
Okay. Just give me a second. So far it is okay, you say. Hmm. Just give me a second, 1 second. This is also there. See, this is also there. Minus delta W reversible. Okay, this is just a sign convention, by the way. It does not matter. So then this will become VDP. Uh, this from just comparing these two equations, this will come. However, note that when I had written this part, no, this del W was work done on the system. When we kind of in textbook, when we define reversible work in a steady flow process, we kind of write work done by the work done by the system, not on the system. Okay.
Yes, yes.
And
Positive, yes. It is positive when work is done.
right. So in this case, actually, it has to be minus VDP or not. Let me check. Indeed, actually, these two quantities also come, to be honest, which I kind of ignored in this case. This will also come. Started hanging. No, it's okay. Essentially, what is this minus sign implying? Minus sign is implying that if you lose kinetic energy, if your fluid stream is losing kinetic energy, then you will be producing work. If you are losing potential energy, you will be producing work. That system will produce work. This minus sign is just to indicate that the work done is by the system, not on the system. Okay, if you're doing positive work on the system, then kinetic energy should increase. That this minus sign is just about that. So just mind that. Okay.
Okay.
This is just the sign convention thing. Okay.
Okay. We can.
So now this is, let me write this part. So at this point, what have we written? At this point, we are writing reversible steady flow process. Only then the expression for delta W will be this. And generally we ignore this, so we write VDP. Actually, wait, this integral will not come. Yeah. So we write this. Okay. You
Okay.
understand?
Okay.
You understand all the progressions? There are a lot of them.
Yes. 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 Besides, I was noting it. So I will see it again. Okay.
Got it. Now let's go back to the slide where we started. Now you will
Okay.
tell me which expression holds when. Now tell me when is delta W VDP or minus VDP.
Minus, as you discussed now, when it is for the reversible steady flow process, assuming that the other entities like KE and PE tend to 0.
Yes, great, amazing. This is kind of so this we will consider soon enough. This we will consider soon enough. Wait, let's keep this. Acha, you tell me generally when will this happen? If we are in this, if this holds true, when will this hold true? What is the extra condition for this to hold true?
For expression number 2,
Yes. Let me, yeah, this is a good point. Should put all of them to 1, 2, 3. Yes. Clearly, if small v is 0, small v is constant across the process, then we can take it out of integral, isn't it?
yes.
Only in that case can we take it out of integral. So this is when v equals to, or let me write sim at least. Makes sense? Either it can be exactly equal, or if it is roughly also constant, then also we can consider it, right? As an approximation.
Okay.
Makes sense?
Right. It's okay.
Now tell me about, so this expression and this expression are identical, isn't it? 2 and 3.
2 and 3.
How
That's
is,
kind of, yes.
now you tell me about this. When is this true?
P delta V. That is just generally for the boundary work that we look.
Okay, but let's say if I'm saying total work is P delta V, then what does it imply?
Okay. Sorry.
No, go ahead, tell me. If it's okay, if it's not
Hello.
if
Sorry.
it's not busy, yeah, go ahead. No issues.
P delta V. Okay. So
I'm saying that the total work. I'm not saying boundary work is P delta V. I'm saying total work is P delta V. What does this say about the system?
it means it should be an isobaric system. Means the process that you are looking at, where the P is constant. We just have to account for the change in volume.
Agreed. Good. It should be isobaric. But there is another thing. There should not be any mass exchange. Remember, I said this part here.
Yes. No mass exchange. Yes.
Only then you can neglect bound. There is no flow work, right? We are kind of neglecting the flow work, right?
Yes. Volume.
right? We are not writing DPV thing there. So flow work is also neglected.
Yes.
We generally don't say that there is a flow work or anything. We generally say that there is a stream, you directly say that the enthalpy is like the energy entering the system is enthalpy rather than energy. You kind of say that way. But note that if work done we are writing as P delta V, essentially there is no mass exchange. Okay.
Okay. No mass exchange. Yes.
If mass exchange is there, we think. If mass exchange is there, then also can we write it? PdV. Then we cannot write it. Maybe then there can be a reversible work also. At least, yeah, there can be VDP work also, right? There can be some reversible work also. If there is a steady flow process, if there is a mass exchange, then this part also comes in. VDP, as we saw, right? We saw in this part, if there is a flow, then VDP work also comes in.
Okay. For mass exchange. Yeah.
Right? So no mass exchange will happen in this case. And this is kind of a similar thing as you mentioned. This is a more general case. So this is okay. And this you cannot write. Wait. This you cannot write ever. You have to actually mention this. As we just saw, you have to mention this. Okay. So I
Okay.
think this is clear now.
Okay.
Now let's come to the problem you asked, Jyotirmaji.
Yes, Reggie.
Which one do you think applies to your process of 1 to 4?
1 to 4. Okay. So 1 to 4.
Or let's wait. Don't even bother to answer that. Wait a second. You tell me. I am saying that this is a steady flow process. So all the processes on this TS diagram are steady flow first of all. So no boundary work. Okay.
Yes.
Now you tell me which case applies from A to B. I'm drawing A and I'm drawing B. You tell me which one will apply. And I'm also okay. And I'm also saying, see, in this case, there are irreversibilities, by the way. Okay. So in this case, actually, you tell me which one, but it is an adiabatic process. Let's say I'm also saying A to B is delta Q is 0.
Okay.
And it is a steady flow process. Mind that it is a steady flow process. Then what is delta W? Tell me.
Well, delta Q is equal to delta U plus dW from first law. Now, so we can use number 6, equation number 6.
Yes, but we actually have to use DH rather than DU. Note that. Because the streams which are entering, they will carry the flow work also. It's confusing,
Yes.
right? Is it confusing?
No, it's okay. But we have to
You
get
realize
the.
that, right? This has come up multiple times in our course also. For streams, we use DH. When you have a constant, what do you say, control mass system, then you use DU, right?
Yes.
If it is a steady flow process, then it has to be DH. Understood?
Yes. It's okay. So
Okay.
okay.
Now you tell me if this were a isentropic process, then can we say what del W will be if it is an isentropic process? A to B. Now you tell me.
Well, then it's an isentropic process. Then we can say MH2 minus H1. It means M within brackets.
Yeah. That was even the case when in the earlier case when it was non-isentropic. Even then it was m dot into delta H.
Delta H.
So that was there in the previous case also. But we
Yes.
can actually write like we can also express what delta H will be. This we can actually expand this when it is isentropic by use of what do you say? By use of TDS relation also. You can quickly see now. Now you will
D
see
minus VDP.
as you rightly said, no.
Yes. So then in that case, DH will be TDS plus VDP.
So then you see DH will become VDP.
Oh,
Is that
okay. Plus VDP. Okay.
understood?
Okay.
Will go to 0 and this will be DH equals to VDP. So this one. Don't bother about the signature sign conventions because here I'm not writing what DH is, what is it in minus out or is it out minus in. So don't bother about that. But you essentially get this, right? VDP. This is what you will use for a reverse because it is an isentropic process. It is a reversible steady flow process. So this will be VDP. Okay.
Okay.
But why can I not write this that V is V delta P? Why can I not write this? Because in the gaseous phase, the density is a strong function of pressure and it will not remain constant across A to B. Whereas if it were a saturated liquids are known to be high density and the density incompressible, right? Incompressible, you
Yes.
kind of say, no, liquid is incompressible.
Yes. Yes.
So densities
Exactly.
don't change with pressure. So this density and this density will roughly be constant. It will not be exactly the same, not exact, but they will roughly, approximately. That is why I wrote approximately here. Only for saturated liquid and for a saturated liquid, a reversible steady flow process, can you write V delta P? That is why in your steam problems, you write pump work as V delta P. So this long story short, this is why we are able to use V delta P in steam problems, but only on the left hand side of the saturation lobe, not on the right hand side. Now you know why this is V delta P.
Yes. Yes. Actually, the density point of view, because it's not constant. But it's
Constant
a
density.
function of saturated liquid only.
But even in this case, see now in this case, when I mentioned for 1 to 4, I'm not sure. Although this incompressibility thing still applies, है ना? But when I was actually when I heard the problem from your end for the first time, I was also thinking, can I say that V4 is equals to V1? Can I do that? So turns out that I can. But we should note that V1 and V4 are not exactly equal. So I'll just have a screenshot of the table just to show that what is going on. For if for 1 to 4, so your negative work, please look at the table. Although the density, see this is the 10 bar. Actually, this is 1 bar. 1 bar, this is the density. And for 0.25 bars, this is the density. And for 1000 bars, I think for 10 bar, I also have to consider 10 bar. For 10 bar, density is this.
Okay.
Wait. For 10 bar density is this. So maybe you can look at the table on your end also, but I'm just showing you the number. For 10 bar, the density is actually very high. It's not equal to the density of 0.25. Okay.
Okay.
These are the two numbers that we will look at. So you actually have to use um, you will have to now you tell me now that the velocities this densities are not same, what will you use? You will use delta W is dH. Okay,
DH. Okay.
understood, Jyotirmay ji?
And
Why DH?
okay. Yes. Delta W. Okay. DH. But there is one thing that the pressure decreases to a back pressure of 0.25, but okay, at constant volume process.
No. We are not talking about volume process. I'm talking about 4 to 1.
Okay, 4 to 1. Okay,
Yeah, we
four
are
to
not
one. Okay,
there. We are talking about 4 to 1.
okay, from 4 to 1. Okay,
From 4 to 1. Okay. See, this is the general expression for a steady flow process. Okay. Now I ask you a question. Say the process is not isentropic, and it is also not adiabatic. If see, even to write this, no, even to write this, that delta W is dH, or as you mentioned, no, m dot into delta H. Even then, you need to say that the process is adiabatic. You can't neglect the heat transfer that will happen. Do you understand this part? So you have to go from the very basics.
okay,
You understand why? So from 4 to 1, what expression will I use? I will have to use the expression delta W equals to dH minus delta Q. Now then I have to assume that the process is adiabatic. So then delta Q becomes 0. If the problem says that there is a heat transfer that is happening during, let's say, pumping, then I have to consider that delta Q also. Then it will become dH minus delta Q, whatever heat transfer that is happening. I have to subtract that from dH to find delta W, work done during pumping. Even for during expansion in a turbine, if this is a diabatic turbine, if there is a heat transfer that is happening, if some amount of heat is leaking from the turbine, then I have to take care of it, and that will, what effect that will have? It will, the work done by the turbine will decrease. You see here, the work done by the turbine will decrease.
yes,
Okay,
okay,
so these things we have to consider. That this is the only thing that I wanted to just emphasize. This is an important thing for people who are looking at this course for the first time. Tend to get confused about this because this is your first time, right? You're hearing this story for the first time, so it's not always like you can't connect all the dots in one go. You kind of require to go through this course multiple times, 2 times or 3 times, and then from different perspectives to realize that everything is connected. So yeah, I think this is the gist of the thing that I wanted to say. So even when you are solving the negative back pressure, negative back work done, no back work that you're calculating, you have to do H4 H1 minus H4 into m dot.
okay.
So that is one. I think maybe with this you can still do the problem.
H4 H1, H4 H1. Okay, okay, I will try it.
Hmm. Now you tell me other questions. What
and
else do you have?
and okay, and just one point that
Hmm.
like generally for the like the exam that we will have, what is like the what is like the pattern? Is there any previous year paper available?
I don't think so. There is any previous paper available as such. At least I don't have an access to one. Uh, yeah, it is generally supposed to be what we have been discussing and very similar to the assignments that you have been doing.
So that means mostly
Nothing
like
very.
one mark or 2 mark questions, not like maybe one question of 5 marks, 8 marks, not like that.
But you have seen the pattern that one question will be there, but
Oh,
it will be 5 marks by the way of five different multi choice, and they all might be connected.
correct.
That
Okay,
could
okay,
still happen,
right. Okay.
just
So
like this
basically,
this question, right?
okay, just like this question, but it will be MCQ type questions only. No like written question like that.
I don't think so. Yes.
Okay. Uh,
Yeah. If you have any other questions, we can discuss that also.
and there was okay. There was just one more question. Maybe I will share.
Hmm.
Uh, this is
Okay.
regarding. Uh, So I have, sorry, it has gone
Okay.
twice.
Oh, no problem.
Okay.
A single acting select. Yeah, you're saying something.
So which formula should I apply? Means, if you can please.
Okay. The correct answer is which one?
Well, in this case, the correct answer is 12.56.
Okay. What did you use? See, from what I can actually guess, like my first instinct would be to write brake power will it be T because it's power, no? So it has to be torque into speed.
And then, yeah. Yes, so
So
basically,
it would be running at some torque.
yes.
It would be some it will have like it will be running at some speed, rotational speed. We have to apply that a torque so that it this um, so we have to apply power such that whatever energy that is being saved in the what do you say in the piston or in the moving disc, now that entire energy has to be dissipated. Now, what is that energy? That energy is essentially torque into speed, rotational speed.
Okay.
From that, so now radius is known. So torque speed is known to us in that case. That is 250 revolutions per minute. How do we calculate torque? Torque I will calculate by saying the torque is actually F into R, right? Force
Okay.
into radius. Crank radius is given to me. How will I calculate force? I will multiply pressure into area. Let's see if we get this thing only or we get something else. This was my intuition. I think this is largely correct. 4 into 10 to the power 5. First thing is that. Uh, then divided by diameter. 4 into area, right? Pi r square. So now r square is uh, zero point 0.1 square, right? Pi r square is the area. This is the force. Now comes the torque now which will be force into radius F into R, and then I multiply with the speed which is 250 revolutions per minute. So per minute is divided by 60 into revolutions is 2 pi. Um, wait, revolutions 250 revolutions. So one revolution is 2 pi. This will be, yeah, this is fine. Then I should get the right answer. What am I getting? 49 something. Let me think what is incorrect here. Torque is F into R only, right? Crank radius is 15 centimeter. Force is pressure into area. So pi R square. Hmm. Mean effective area is force. 4 diameter of the piston is 20 centimeters. How how did you get 16.37 if you got something?
Well, actually, I got a separate value. It is not exactly 16.37, but I was getting close to like 15.7. So means
Oh,
of the options that we look, it seems that this is the most closest. So that's how I had given it. So in that, if you see that we have the values like the pressure we know, piston diameter we know, crank radius. So basically R is given to be 15 centimeter. So and on the stroke length, that's also we can find out from the formula twice R. And that's what I assumed. And then the speed is given as 250 RPM. Somewhere it is written. Yes, 250 RPM. And in gel is, if it is single acting, then I can say N is equal to 1 maybe. So from the piston area we calculate. From there we can, there's the formula of the indicated power. That is P mean into L into A into capital N into small n upon 60. And from there we can, means basically, and then we compute the product. And from there I was getting like 15.7 kilowatt. So means I'm not sure how to solve this. So that's what I was
okay.
thinking.
Okay, let me check. Let me check. Mm-hmm. Stroke is 2 hour. Okay, wait. Okay, okay, this should not be there. Okay, so your answer is 15.7 is correct actually. 12.56 might be a wrong answer. The way you have done it is correct.
Okay, then okay, just to
Yeah. Crank radius is, wait, crank radius is, okay, fine. Hmm. Okay. So that will give you stroke length. So this is the mean. Okay, that is okay, fine. Force into R. RPM. That's okay, I think. Every revolution you do this. Okay, fine. Hmm. That's okay. Hmm. Yeah. Do you have any other doubts?
no, actually, so far it's okay.
Hmm. Largely, I think we can close in 10 minutes because large amount of time we have taken today on our discussion, which is good. Maybe I will solve few questions. Let me see. Maybe because you are there, maybe would you like to solve few questions?
Yeah, let's go. Maybe one, two we can take.
So tell me this one.
Pressure ratio. Okay. Cutoff ratio. Cutoff ratio. Cutoff ratio. Just a second. Diesel. Okay. Compression ratio. Is the cutoff? Compression ratio is cutoff diesel. Return pressure ratio. I think number one part C or number three should be okay.
Hmm. Wait, number three you are saying, is it?
Yes, pressure ratio Breton cycle, compression ratio is auto, and cutoff ratio should be diesel.
Wait. Cutoff is. Hmm. Yes, that's correct. That's correct. Yes. No, okay, fine.
Stage compression process, multi-stage compression process, compression rates. Stage compression, Breton cycle, Breton cycle, Breton cycle. Multi-stage compression process. Okay. Well, it can be three part number one.
Backlog ratio increases.
I mean, because now it's a multi process, so the pump work cannot be neglected, right? Without
Yeah, but
degradation.
intercooling is also there.
Okay. Intercooling is also there. Okay. Then what? Then maybe.
Don't guess. If you know how to do it, then
So
we can
this one
discuss.
actually not clear to me. Number three.
Okay. See, when you do intercooling, no, multi-stage intercooling. Okay, let's discuss this and then maybe we can try to close. Suppose, see, there are two ways to reach, and this is essentially, see, oh, say you isentropically reach from P1 to P2. That is one way to do it, right? You're compressing. But you can take another approach. You can go this way, and you can still compress the fluid, isn't it?
Yes. P2 is increasing.
And if you have done that exercise, it's a very well established exercise. The minimum reversible work done during compression is through an isothermal process. Do you recall?
Yes. Maybe.
And that is why intercooling is done. Intercooling kind of mimics that. So what will happen in intercooling? Something of this sort will happen. You will go up, cool to intermediate pressure, then come down. Then you will compress, and then you will come down, and so on. So you will keep cooling so that your outlet compressor inlet pressure every time you compress is the same. So during basically the idea is that during multi-stage compression with intercooling, no, you're kind of reducing the temperature the temperature over which the compression happens. Your net the temperature rise is lower, and because this has minimum like you kind of decreasing the amount of work done during compression, so your compression work decreases, so your back work ratio actually decreases and your thermal efficiency increases.
Okay.
Also decrease, wait, decreases, thermal efficiency should increase, man. Wait, what is this? Check, because this portal says thermal efficiency should also decrease. What as far as I know it should increase, but let's see. As I wait, let me also check. Thermal efficiency decreases. Okay, thermal efficiency decreases by. Okay, yeah, thermal efficiency will decrease. Okay, let me pull up that part. I was also not clear to this. Okay, Thermal efficiency decreases, it seems, which is correct. Okay. So back work ratio will decrease. Okay. Because
Okay.
compression work is going to decrease. That is there.
And thermal efficiency
So
will
this
also decrease.
thermal efficiency will decrease.
Okay.
Thermal efficiency is decreasing because you are increasing the heat rejection to the ambient. Okay, so you see here, if it would have been like this, if it would have been like this, you can kind of visualize why work delta H, like H2 minus H1 plus H4 minus H3 is lower than H1 minus this whatever HX is or HY is. This is a much higher thing. But you see that the Q out increases for the same Q out increases, right?
So okay.
And for an ideal, huh?
Yes, yes. Q out is increases.
So because Q out is increasing, and if we calculate and if we see the increase in work done is not that much, so that it can actually increase the efficiency for an ideal gas. So this is the relation, right? W, what is it? W by Q in, isn't it?
Yes, yes. Or
So
maybe
this
Q
will be
in, Q out upon Q in. Yes.
Q out by Q in, right? So now you see that Q in remains same. Q in is not changing, but Q out is increasing. So thermal efficiency will decrease.
Hmm.
Q in is same, but Q out is increasing. That is why thermal efficiency decreases. Okay.
Okay. Okay.
Okay, let me see if we can do one more question or should we close? Okay, we can look at this question and then just close. Can you tell me this one?
Ideal auto cycle with a specified compression ratio is executed using different. Pick the correct option for which the thermal efficiency to be highest. I mean,
So pull up the expression for thermal efficiency of an auto engine from the book or wherever.
yes, for the auto engine, if we look, then the thermal efficiency is okay. It is here. Correct. Uh, thermal efficiency is simply 1 minus 1 upon compression ratio to the power gamma minus 1. So it depends on the compression ratio, and that too compression ratio is the ratio of, we can say, the V3 by okay. So it should be, it seems to be independent of the working medium.
Is it? What are, look at it. Look at it.
Gamma. Okay. No, no, no. Yes, compression ratio 1. Yes, 1 minus 1 by compression ratio to the power gamma minus 1.
Hmm.
Okay, so gamma value we have to check here. Then
So it turns out the gamma value of argon is the highest. Now, because gamma value of argon is the highest, this denominator will be the highest for argon, and
yes,
because this will be highest, this negative term will be the least for
least.
argon, and so thermal efficiency will be highest for argon.
Okay, it means that we have to check the value of gamma. Okay,
That you have to check.
okay.
It is not given in this example, but generally, I don't think we someone would expect people to remember the gamma values of these gases. Okay.
Okay.
In exam, maybe it will be given or something.
Okay. Gamma. Yes.
Right. So yeah, I think for today we can close. We had a good discussion today. And I think we are just 2 weeks away from your exam. Is that right? 2, 3 weeks away.
Yes. Yes. Just 3 weeks away. So, any suggestions from
Okay.
you, like how to overall prepare?
Not sure because see, it's very different from a typical engineering course offline. The way I have seen these things are you essentially solve multi uh, this multiple choice questions only. But I guess just revision of the fundamentals will help. And numericals, just whatever book you are referring to, just just repeat all the or try to repeat as much as the as much as of the numericals solved numericals of the chapters. Don't go like if you can definitely solve unsolved numericals, but I would say start with the solved numericals, solve every numerical, try to solve every numerical, or at least the good ones. I think that would be enough, more than enough, I feel.
Okay. Okay, Shaji.
Yeah. So, Jyotirmiji, thank you for attending. Let's meet next time. That will be our last session. Let me see if I will try to sum up things or just continue with this problem solving, and then we'll close for this semester. So, yeah, nice to connect, and yeah, let's meet next time. Thank
Okay.
you.
And also, thank you, Shreji, a lot for your patience and your efforts. Thanks a lot.
Thank you. Thank you so much.